All right, so there are several different definitions that have developed throughout history for acids and bases. So we're going to start with the most simplistic, and then we're going to work our way up, okay? The most simplistic happens to be the one that was, you know, thought of first. So Arrhenius came up with the idea that acids produce hydrogen ions when dissolved in water, okay, an aqueous solution, and bases will produce hydroxide ions, okay. So when you put them in solution, if it's an acid, you've got an H plus ion floating around in there, and if it's a base, you've got an OH minus ion floating around in there, okay. All right, so down here you see that basically, according to Arrhenius, the acid had to have the hydrogen on it to begin with, and the base had to have the OH on it to begin with. So that's going to help us identify acids and bases. Acids will have an H, bases will have an OH. All right, so now we're going to practice writing the dissociation equations for the following according to the Arrhenius model. All right, so here we have HF. That would be an acid, okay, according to Arrhenius's definition, which means that it would break into an H plus and an F minus when you threw it in solution, okay? So because the H is a plus, then the F has to be a minus because over here they were neutral. So your charges should balance on both sides of the equation. All right, here we have an OH we see, so this is going to be a base according to Arrhenius. So we're going to get a K plus and an OH minus, okay? All right, down here, this is still our acid, and here we have water, okay? So in this example, basically, they're wanting us to show the same thing, but now, instead of just showing the hydrogen ion, we're going to show it actually attaching to the water and making the hydronium ion, okay? So we have a H3O plus, and then an F minus, okay? So in this case, we're showing hydronium. In this case, we're showing just the hydrogen ion. All right, the next model is Bronsted-Lowry's model. All right, his model is based on the accepting and donating of protons. But wait, I thought protons defined an element. Well, they do, but when you're thinking about a hydrogen ion, a hydrogen atom, excuse me, let's talk about the atom first. Hydrogen atom has only one proton, no neutrons, and then one electron. When it loses that electron, it becomes the hydrogen ion, which is H plus. Basically, all that is a proton, okay? So when he's talking about donating, accepting of protons, he's basically talking about a hydrogen ion, okay? It's just same thing, but calling it by a different name, okay? All right, so in his model, acids are proton donors, or H plus donors, and bases are proton acceptors, or H plus acceptors. Okay, so down here, we have HF. It has an H, so we know it's probably going to be an acid. And the HF is going to give its H plus to the NH3, which is going to be accepting it, so that's the base. Okay, and then it's got the NHF and the F1 minus. Okay. All right, now something interesting happens with Bronsted-Lowry, okay? Now, you see this little symbol in the middle here. That indicates that we are at equilibrium, okay? So this little symbol is telling us that the reverse reaction can happen as well. So if you think about it from the reverse, okay, so after the base has accepted the H plus ion, and now the F minus is by itself, now the reverse reaction, the NH4 plus is going to donate the hydrogen ion to the F minus, okay, to form these again. So basically, the NH4 plus is acting as an acid on this side as the proton donor, and the F minus is acting as a base, which is the proton acceptor, okay? So basically what happens is, according to the Bronsted-Lowry definition, once you have an acid and it donates an H plus to the base, The base then possesses that H plus, so it's now the acid, so to speak, pseudo acid, we'll call it, the fake acid, because it can now donate that H plus back to the thing that was left over from when the acid donated the H plus. Okay, so it's a reverse reaction. We call these conjugate pairs. Okay, so when an acid donates an electron, it shouldn't say an electron, it should say proton. That's my bad. So when an acid donates a proton, it becomes a conjugate base. And then when the base accepts the proton, it becomes the conjugate acid. Okay, so let's look at this. Okay, so here we have our base, NH3, and our acid. Our acid in this case is going to be H2O. H2O is going to give H plus to NH3. Okay, NH3 becomes NH4 plus, and the OH minus is left over. Now the reverse reaction, okay, the NH4 1 plus can donate that OH back. So basically, the base became the conjugate acid, and the acid, when it lost its proton, became the conjugate base. Okay, so let's practice some of these. Okay, so it asks us to complete the equations, and then we're going to label. Okay, so first let's go on completing. Okay, so we've got, here's an H, so that indicates to us that this is probably the acid. So it's going to lose that. It's going to come ClO2, and it's losing an H plus, so now it's minus. And then the H2O is going to accept that H plus and become H3O plus, okay, the hydronium ion. So minus and plus, and then over here it's neutral, so neutral on both sides. Okay, so this was the acid. The acid turned into the conjugate base. Okay, and in this case, water was acting as the base because he accepted that H plus. So now the hydronium ion is the conjugate acid. Okay, look at the next example. Okay, in the next example, the H plus is going to come from the water. Okay, so the water is going to give that H plus to the OCl minus, so it's going to become just HOCl because you had the H plus and the minus on that, so they canceled. And then the H2O becomes OH minus. Okay, so you have a minus on this side, minus on that side. It's all good. All right, this is a base, okay, because it accepted the proton, which makes it over here the conjugate acid because now it can donate it back. This acted as the acid because it donated the H, and then this then becomes the conjugate base because it can now accept the proton, okay? All right, now last example, okay? The H is probably going to lose the H plus, donate it, so it's going to become Cl minus, and then the other one is going to become H3PO4. Okay, so we got a minus and a minus, so we're balanced. So this was the acid, and then it became the conjugate base. This was the base, and it became the conjugate acid. Okay? All right, so what relationship could you draw about the relationship, what conclusion could you draw about the relationship between the strength of the acid base and its conjugate pair? So let's look back, okay? So here, HCl, okay, these are conjugate pairs, okay? All right, so with HCl, let's say that the equilibrium was very strong, okay? So we'll say we have a very high K, for the forward process on this one. So we'll call it KF, K forward, okay? And we'll say it had some ginormous value, okay? Something like this, okay? If that is the K, that means that it proceeds towards completion, okay? It's very strong, okay? That's what we would consider strong. Now the Cl then, when it's acting as the conjugate base, if you reverse the reaction, what do you have to do to KF? Well, you have to inverse it. Okay, so the reverse reaction is going to be, so we'll call this K reverse, okay, is going to be 1 over that. So this is a teeny tiny number. So the stronger the acid or base, the weaker the conjugate pair is. Okay, So let's write that. So the stronger the acid or base, the weaker the conjugate pair will be. Okay, and vice versa. If you start with a weak acid or base, then your conjugate pair will be strong. All right, so let's talk about what water's doing in these reactions. Is it acting as an acid, as a base? How about both? Both would be the correct answer. According to Arrhenius, though, water would have been neither an acid or a base because only 1 to 2 in 10 million water molecules actually make an H plus and an OH minus. And then in that case, you could really call it neither, according to Arrhenius. Bronsted-Lowry would have called water, though, amphiprotic, which means that it can accept or donate protons. Nowadays, we call it amphoteric, which means it can act as an acid or a base. So let's talk now about the Bronsted-Lowry definition versus the Arrhenius definition. How is the Bronsted-Lowry definition broader than the Arrhenius definition? Well, the Arrhenius definition restricts us to dissolving things in water. Bronsted-Lowry does not, so we can now talk about reactions that occur in other phases. Bronsted-Lowry also recognizes that a proton cannot be donated unless there's a substance available to accept it. So, according to Arrhenius's definition, an acid just made H pluses in water, but now we know, according to Bronsted-Lowry, that there has to be something there to accept it, even if that be a water molecule. Okay. It also, in different situations, a substance can be either a proton donor or a proton acceptor, according to Bronsted-Lowry definition, which is more closely associated with how real chemical equilibria works. All right, the last type, or the last model for acids and bases is called Lewis model. Okay, and basically the little slogan is "Have pair, will share." Okay, from Lewis base. So in his model, acids are electron pair acceptors and bases are electron pair donors. Okay, so in this first example, you see H plus and then you see NH3. Okay, H plus is going to combine with the NH3 to make NH4 plus. In this example, the H will be, because he's a plus, he will accept the negative electrons. So he is going to be the acid. And the NH3 is going to donate those protons to him. Okay, it's going to share them with him. So that will be, he will be the base, okay, in this model. All right, here is another example, okay. Here we have an NH3 molecule again and OH minus molecule, okay? Now, NH3 is ammonia, and it has 4 pairs of electrons around it, and 3 of them are shared with hydrogens, okay? Therefore, this extra pair is available to donate, making NH3 a base, according to Lewis, okay? Now, OH minus, okay, he has 4 pairs of electrons around his central atom, and only one of them is shared with a hydrogen. His unshared pairs of electrons will therefore be available for donation to an acid, so he is considered a base as well, OH minus, okay? So this model does fit with Arrhenius and Bronsted model, according to the OHs and such, okay? All right, so here's a little schematic that just kind of shows the progression, but basically Arrhenius is the simplest model, H plus donor, OH minus donor. And then Bronsted-Lowry, he kind of moves it up, H plus donor, H plus acceptor. And then Lewis takes us even further with electron pair acceptor and electron pair donor, okay? So basically, the more out you go, the more substances can be encompassed and described in terms of acid-base.